All right, I wanted to talk about your quiz a little bit. There was quite a bit of confusion on the quiz, and so I just wanted to run through it. These are the solutions, and I'll post these. So, but I just wanted to look at the problem together. So we're supposed to determine if this series diverges, converges conditionally, or converges absolutely. And you should notice right off the bat that it's an alternating series, right? When k is odd, the terms will be negative. When k is even, the terms will be positive. So for an alternating series, the first thing you need to do is test for absolute convergence. So a lot of you jumped straight to the alternating series test because you saw, oh, it's an alternating series. I'm going to jump straight to the alternating series test. And maybe the reason that you do that is because you're thinking, well, if the series is not, if the alternating series diverges, then it's definitely then the how should I say this? So maybe your thought process is this. Maybe you're thinking, if this series diverges by the alternating series test, then the absolute value of this series is definitely going to diverge as well. But your thinking there is backwards, okay? It's possible for a series to fail the alternating series test and yet still be a convergent series, still be an absolutely convergent series. So here's an example of that, because I didn't just want to state that without giving you a concrete example, right? So you take a look at this series here. This is an alternating series, right? When k is odd, the terms will be positive. When k is even, the terms will be negative, right? And it's absolute value of sine k over k squared. Now in the alternating series test, you have to establish two things. First of all, you need to establish that the non-alternating part, right? In this case, the absolute value of sine k over k squared is decreasing. And then second of all, you need to establish that limit as k approaches infinity of absolute value of sine k over k squared equals 0. Now this one you can show. The second condition is pretty easy to show. You can use like squeeze theorem. You can say, well, absolute value of sine k is between 0 and 1 for all k, and limit as k goes to infinity of 0 over k squared is 0. Limit as k goes into infinity of 1 over k squared is 0. Therefore, by the squeeze theorem, limit as k goes to infinity of absolute value of sine k over k squared is 0. Right? So that condition holds. This condition, however, does not hold. And because sine k is going to alternate between 0 and 1. And in fact, if you look at this thing in Desmos, you'll see it's not a decreasing series, right? It bounces forever. So it's not a decreasing series. It's not even eventually decreasing. And so since that condition is not met, you would say the alternating series test, well, you wouldn't say necessarily that the original series diverges. You would, because you haven't tested for that yet, right? All you've shown is that the alternating series test, if the absolute value of the series diverges, then the alternating series test here would conclude that because this condition isn't met, the series diverges. But it's possible that the series converges absolutely, right? In which case, you need to check for absolute convergence. So in this case, we would check for absolute convergence by taking the absolute value of this original series, right? And you would just get the absolute value of sine k over k squared. And that thing, you can show that this thing converges by a direct comparison, right? You can say absolute value sine k is less than 1. So absolute value of sine k over k squared is less than 1 over k squared. This thing converges Since the larger series converges, the smaller series also converges by direct comparison. So actually, this series is absolutely convergent, even though it fails the alternating series test, but it's absolutely convergent. And so if you were to just run the alternating series test and see that, oh, the alternating series test fails, therefore the series diverges, you'd be wrong, because the series actually does converge, right? So when you're confronted, the moral of the story is this. When you're confronted with an alternating series, the first thing you check for is absolute convergence, which means you should do this step first, right? Because look at how much work you save. If I do this step first and I determine, oh, the series converges absolutely, then I don't even need to run the alternating series test, right? Whereas if the series diverges, then that's when I would then that's when I would go to the alternating series test to see if maybe it converges conditionally, right? So let's see. So if the absolute value of the series converges, then you're done. You know the series converges absolutely. If the absolute value of the series diverges, well, then you need to run the alternating series test to see if it converges conditionally, right? But if you only run the alternating series test before you check for absolute convergence, then you could falsely conclude that the series diverges when in fact it converges absolutely. Now that's not the case here, but because this is a conditionally convergent series. But still, you need to check for absolute convergence first. Okay, so let's talk about that a little bit, because one of the most common mistakes I saw in this test, and this was or this quiz, and this was very disheartening to me, is that a lot of you, you said, okay, yeah, I'm going to look at the absolute value of the thing, I'm going to get this sum, right? I'm going to get this thing. And then you said, okay, so I'm going to take limit as k goes to infinity. In fact, some of you said that this was equal to the limit as k goes to infinity of ln of k over k, and that's just not true, right? This is a sum, right? The sum is not going to necessarily be equal to the limit of the terms of the sum. So no, don't say it equals that. But a lot of you did this. You said, well, I'm going to look at the limit as k goes to infinity. And then you said, by L'Hopital's rule, because this is infinity over infinity, right? So I can apply L'Hopital's rule. Derivative of ln of k is 1 over k. Derivative of k is 1. And you just get limit as k goes to infinity of 1 over k, which equals 0. And then, so you do get 0 there. And so a lot of you said, so the series converges. But that's wrong. Okay, because what test are you applying here? The test you're applying here is the test for divergence. And the test for divergence is inconclusive if you get 0, right? It's inconclusive. So what we've shown basically is that the series could converge or it could diverge. We still don't know. We're not any better off than we were before we ran this test. So you have to choose a different test to show whether or not the series converges or diverges. Absolutely. Now, it turns out that the series does diverge absolutely. There are a couple ways you could show it. You could run a limit comparison test. You could do the integral test. I did a direct comparison test. Okay, but in any case, you should get the same conclusion, which is that the series diverges, right? It diverges absolutely. But then it could converge conditionally, and you would establish that by running the alternating series test. Now, this is the second thing that I wanted to talk about, okay? Because a lot of you went through the motions correctly, right? You showed that it diverged absolutely first, and then you went to the alternating series test. But then you didn't actually prove these statements. You just wrote the statements. You just claimed, like, a priori that ln of k over k is decreasing, right? And then you didn't show it. You need to show it, right? You need to show it. So way back in like 9.2, there were 3 tools that we said that you could use to determine if a sequence is monotone. So one of them is that you could look at a ratio of consecutive terms. And if that ratio is less than 1, then the sequence is decreasing. If it's greater than 1, then it's increasing. You could look at a difference of terms. If the difference of terms is is greater than 0, then the sequence is decreasing. If it's less than 0, then the sequence is increasing. Or you could treat the sequence as a function and apply the first derivative test to determine if it's increasing or decreasing, right? And that's what I chose to do, because I tried to look at a ratio of terms first, and what you end up with is something like k times ln of k over k plus 1, or no, what was it? You end up with k times ln of k plus 1 over k plus 1 times ln of k. And then showing that thing is you know, somehow less than 1 is difficult, right? It's not an easy thing to do. So anyway, so I chose to do this. So you take the derivative of this function, and you're not applying L'Hopital's rule now. You're actually going to take the derivative of the function, right? And then here you can say, well, the denominator is always positive. The numerator is going to be negative for any x large enough, right? Eventually, ln of x outgrows 1. In fact, it outgrows 1 at e, right? ln of e is 1. So for any x greater than e, the numerator is 0, or the numerator is negative, right? So this thing is negative for all x greater than e. This thing is positive for all x, and so the derivative is less than 0 for all x greater than or equal to e, actually. But we can definitely say that for any x greater than or equal to 3. Anyway, so that's how I showed that. And then for the limit, most of you did the limit correctly. But yeah, again, there's just a lot of confusion. So let me just say again, right? When you're dealing with an alternating series, do not jump straight to the alternating series test, right? The alternating series test could falsely lead you to assume that the series diverges when in fact it converges absolutely, right? So don't jump straight to the alternating series test. You have to check for absolute convergence first, and then once you've established absolute convergence, then you can, or actually, if you establish absolute convergence, then you're done. If you establish absolute divergence, then you go to the alternating series test to see if the series converges conditionally. Okay, so those are the steps, and again, I'll post these solutions in the normal place so that you can look at them and make sure that you've got the idea. But I just wanted to address some of those things that I saw. Very few of you did this problem correctly. In fact, I don't think anybody did it totally correctly. I gave a couple of you full credit if you did the alternating series test first, because we hadn't really talked about why that's a bad thing. In the future, if you see an alternating series and you jump straight to the alternating series test, I will mark you down for that in the future, because you've now been warned that that's not legitimate, right? You have to establish absolute convergence first. But anyway, yeah. So if you have any questions, please respond to this announcement or post a question on a discussion board or something, because yeah, obviously you are not quite getting the picture here.